Hi everyone, welcome to the video lecture on Unit 3 Mechanics of Continuous Media Part 6. The learning outcome of this video lecture is to derive the expression for depression of cantilever with an end load. A horizontal beam with its one end rigidly fixed and loaded its other end is known as cantilever. Consider a thin, uniform and light beam of length L clamped at its one end A and loaded with a load W at its free end. In the diagram, AB is cantilever. With no load, the cantilever is in horizontal direction AB. When load W is applied, the cantilever is bent and the bent position is shown as AB dash. LB the length of the cantilever. Let the end B be depressed to position B dash under the action of the load. Let us take a section of the beam at P, distance x from A. In the diagram, P is the section, it is at a distance x from end A. Now, consider the equilibrium of part PB dash. PB dash means this part. Consider the equilibrium of part PB dash. Since the beam B fixed at A, the load W at B dash exerts an axial torque tending to rotate the beam clockwise. Clockwise means along this direction. Now, the magnitude of this torque is equal to force into distance, that means load into elongation, W into L minus X. The magnitude of this restoring torque is equal to, that is bending moment is equal to Y by R into I, where Y is the Young's modulus of the middle of the beam, I is the geometrical moment of inertia of section P, and R is the radius of curvature of the bent beam at P. At equilibrium, W into L minus X is equal to Y by R into I. If Y be the depression at point P, then the radius of curvature at this point is given by R is equal to 1 plus dy by dx whole square whole power 3 by 2 by d square y by dx square. In this case, the derivation of this radius of curvature is not necessary. Since y is small, dy by dx whole square can be neglected in comparison to 1. Hence, the radius of curvature R is equal to 1 by d square y by dx square. That is equation 3. From equation 1 and 3, we get W into L minus X is equal to Y by R into d square y by dx square, or d square y by dx square is equal to W into L minus X by yi. That is equation 4. Integrating this expression, we get dy by dx is equal to W by yi into Lx minus x square by 2 plus C1, where C1 is integration constant. The integration constant C1 can be determined by applying boundary conditions. The boundary condition at A of the beam is at x is equal to 0, dy by dx is equal to 0. Then C1 is equal to 0. Therefore, dy by dx is equal to W by yi into Lx minus x square by 2. That is equation 5. Again integrating equation 5, we get y is equal to W by yi into Lx square by 2 minus x cube by 6 plus C2, where C2 is another constant of integration. This constant C2 can also be determined by applying the boundary condition at the end A of the beam. At end A of the beam, that is at x is equal to 0, y is equal to 0. So the integration constant C2 is equal to 0. Therefore, y is equal to w by yi into lx square minus by 2 minus x cube by 6. That is the equation 6. At the end B, that is when x is equal to L, the depression y is maximum and is equal to delta. Therefore, delta is equal to w by y into L cube by 2 minus L cube by 6. On solving, we get depression delta is equal to w L cube by 3yi. That is equation 7. Special cases. For a beam of rectangular cross section, the geometric moment of inertia I is equal to BDQ by 12, where B is the breadth and D is the thickness of the beam. Now the depression delta is equal to 4W L cube by Y BD cube. For a beam of circular cross section of radius R, the geometrical moment of inertia I is equal to pi r power 4 by 4. On substituting the value of y in equation 7, we get the depression delta is equal to 4WL cube by 3y pi r power 4. That is equation 9. In this way, we can derive the depression of a cantilever in case of rectangular cross section and in case of circular cross section also. Thank you.